This is chapter 7, the second part of the recording, and we are talking about crystalline dislocations, how they move through the crystal structure, how they are related to changing the properties of the material. That's why we say strengthening, but really it's not just about strengthening mechanisms, but it's about changing the properties. How this crystal structure and the distortions that we put into it change the properties of the material. So let's look at a concept first called anisotropy or anisotropic behavior in crystalline materials. We can induce this by squeezing a metal plate thin. Before you roll, and we call it rolling, which is moving that plate through a series of rollers and squeezing it together. Before doing that, you'll notice that our crystals are, reasonably the same size. They're reasonably similar shape as well. They're random and they're all approximately the same dimensions. This is what we're going to call isotropic. It's going to create isotropic behavior, meaning that if you pull this material, really, I should say, if you test this material in any direction, the behavior is going to change. Not change. If you cut a specimen out, say in this direction, and you pull it in tension, the material properties that you experience or that you observe are going to be the same as if you cut it out in the opposite direction and test it in tension there, because the crystals are approximately the same in all the directions. Now, once we roll this material through and we squeeze that material out, it becomes longer, it becomes thinner, it becomes wider. And as a result, what we're really doing is we're changing the crystals. We've rolled it through a series of rollers. If you had this plate and a couple of rollers, and you're turning it in this way, your movement is in this direction. You're squeezing and thinning out the material, and the crystals themselves are actually becoming elongated. And now the dimensions, or not the dimensions, but the behavior, if you cut the specimen out in that same direction that we indicated before, and if you cut it out in the opposite direction, these crystals and the way those dislocations move through the crystal structure are going to be very different. And you're going to see different properties. It'll be stronger in one direction than another. As a result, this effect is called anisotropy, or we call it anisotropic behavior. So we're going to look at an example of this anisotropic behavior. We're going to look at the material tantalum. Tantalum is an element, Ta. It has atomic number 73. Atomic mass, I'm going to shorten that for 181. And it's named after a Greek myth about a villain named Tantalus. So that would be an interesting side note. Anyway, tantalum, this material, we are going to look at a cylinder of tantalum that's been machined from a rolled plate. The rolled plate is fed from this left through the rollers to the right. They set the roller distance such that the final thickness is what they want it to be. Of course, it's smaller. Now, I've exaggerated this here. Really, the final thickness is always going to be smaller than the initial. but it's not going to be quite this much. Anyway, we've rolled it in this direction, so this rolling direction is in fact the one that I've shown here. And that means that these crystals have elongated out in such a way that they are now longer in this direction than they are in the opposite direction. Before, over here, you would end up having those crystals that were all approximately the same size and the same shape, but now they're going to be elongated in some way, shape, or form. Okay, and so we take this cylinder and we put it in some sort of a firing mechanism and shoot it at a target. I'm going to go ahead and erase some of this so that we can have a clean slate to work on here. Okay, so we fire this cylinder from this orientation. These crystals are still in this direction, and the end result, we get a deformed cylinder that looks like this picture over here on the right. Interestingly, the dimensions of this cylinder are not the same in multiple directions because the material has behaved differently. These two different diameters are different. Instead of getting a circle, we're ending up with, or a circular cross section, we now have an oval. Okay, the plate thickness direction is indicated here. And we see that this material certainly did not behave isotropically. Okay, let's move on a little tiny bit. Oh, by the way, here's tantalum. It's found in these particular countries of the world, not here in the U.S. So the question then becomes, how do we start to utilize this information in order to, let's say, strengthen a material? If we wanted to use this anisotropy to be able to, and the behavior of these deformations moving through the material in combination to be able to increase the yield strength or the ultimate strength of the material. So we're going to talk about 4 different strategies. The first one is we're going to reduce the grain size. If we reduce the grain size, and we know that the grains themselves, the boundaries of those grains are in fact the barriers to slipping, we have more inherent grain, say, length in any given volume of material, and so we're going to increase the strength. We also know that the strength or the barrier strength increases with the increasing angle of misorientation. When we have more of those angles of misorientation from what we would call perhaps the testing angle, then we're going to have a larger number or a larger strength represented from the behavior. The smaller those grains, the more barriers there are to slip, and the more of them there are, we have more barriers overall and have a higher likelihood of more misorientations. Additionally, I just want to point out here that we can see the slip on a slip plane where we have this extra plane of atoms in the crystalline structure, and we have a missing plane of atoms, that as that moves through and those boundaries here are broken and become boundaries here, nope, moves the other way, sorry. Those will be broken, and the new boundaries or the new bonds will become here, will have this particular gap move over. And as that continues to move over and over, once it hits this boundary, it stops. And that's the strengthening mechanism. Okay, let's go ahead and look at the second one. We call this one forming a solid solution. Okay, we've talked in previous chapters about those impurity atoms and how they can be put in, and we can calculate the percent impurity. But what happens when those impurity atoms are in there, whether it's a tiny atom, like the one shown on the left, or if it's a big one on the right, what's interesting is the lattice structure has to change because those are not the same diameter atoms any longer. Those distortions act as barriers, okay? Because as we have the motion of, we're going to look at this particular slip plane, and let's just say we want it to move in this direction, the dislocation to move that way. As we move bonds and we recreate bonds, if we cut those bonds and we make them with new atoms, and then we want to do it again, the problem is that for the second set, what are you going to bond with in this location? It's not going to bond in the same way, the same amount, and so that will be a barrier or a hindrance to this movement happening. Also, you can see that these lattice strains involved are, in this case, it's smaller, and so they're kind of, bowing in, and that's going to create an impedance to this moving through the system. Similarly, over here on the right, as you move through, let's say D is going to the right, these stresses an interesting phenomena where when you have a small impurity that you've introduced into the system, that the locations where you have the extra plane of atoms, which had like this extra space almost, those little atoms want to congregate there. They concentrate themselves in those regions, which are regions of compressive strain. And this is a partial cancellation of, I'm going to circle that because that's kind of interesting. A partial cancellation of the dislocation compressive strains. All right, so we have the two acting against each other. This creates a reduction in mobility because these dislocations don't want to move. They're also filled up and they don't need to. And you get the resultant increase in strength. I want to point out that, this was the region of compression. This side of the dislocation is the region of tensile stress. And so small atoms will tend to be on the compressive side, whereas the large atoms would tend to congregate on the tensile side. Oops. Okay. All right, so that's the general behavior properties. Okay, so let's look at our third strategy for strengthening. We're going to call this one precipitation strengthening. Okay, so let's look at first, what do we mean by precipitation? A precipitation in this case is not an atom. This is not an impurity in the crystalline structure, but rather this is molecules, almost regions of multiple molecules that interrupt the lattice structure. Okay, we have a different material inside the lattice structure, and the harder these particular regions are, the stronger they are they make it more and more difficult for the dislocations to shear off that particular material to move through. If a precipitate or a dislocation is moving through a material, when it reaches the precipitate, first of all, it is a boundary, and so they'll tend to stack up there, but as the stress increases, that precipitate will eventually shear off and the dislocation continue to move. Okay, you need large shear stresses to do this. You have to shear off that material. If you're looking at this, this is kind of the side view, and if you look at it from the top, you'll notice that the precipitate, because it's sheared off, some of it carries along within, one half of the plane, and the other stays pinned where it was. I should say, I'll just leave it like that. So this one continues to move. And we have maybe an average distance S spacing between these different sites where you have the precipitates. We're calling those sites pinning sites. And we have a distance of S. As a result, we're going to end up increasing the yield stress approximately as a ratio of 1 over the spacing. Here's an example of this particular precipitation strengthening. This is an airplane wing, and they use this aluminum, but aluminum tends to deform easily. We like that in some ways because it's very light, but the deformation needs to be stiffened up also, and we can use precipitation strength precipitates inside it using a ceramic, usually, or an alloy, a metal alloy, either way, inside the material. So each of these different little black dots within here are that precipitate, and you can see them. Okay, we will keep going and look at our fourth strategy. This one is called cold working. Okay, in some ways we can also call it strain hardening. Now, cold working, we've already defined that as being deformation of a material that is below the recrystallization temperature. Okay, we've already defined cold working to be deforming a material below the recrystallization temperature, which can be very hot. In this case, where we call it a room temperature, I don't think room temperature is exactly the right way to say it. It's technically any temperature below the recrystallization temperature. So we'll just call it a lower temperature. It doesn't really have to be low. It can be still very hot. But we're going to go ahead and work that material and either pull it or squeeze it or roll it or some sort of a method. And what that's going to do is that's going to strain the material. It's going to create those elongated crystals, or maybe I should say deformed crystals. Generally that anisotropic behavior. And we will see an increase in the yield stress and the ultimate stress for that material. Now, below here, I've shown 4 different common manufacturing methods that will reduce the cross-sectional area. How can we do this? We've already talked about rolling. That's the third one over here. The rollers squeeze the material from an initial thickness, or here we're using cross-sectional area, to a thinner section. Many times these manufacturing methods are going to require many rolling mechanisms to achieve the final desired product. So you don't go from, say, a 1-inch thick plate to a 1/2-inch plate instantly. You have to go through a series of rolling, where each incremental rolling, each rolling mechanism will create an incrementally smaller thickness. Okay, so that's one. Kind of the let's see. Let's look at forging. We'll look at forging over here on the left. This is where we have a die, otherwise sometimes known as a form, something that is in the shape of the final product that you want. If you put a piece of material, where we're calling it blank here, into the die, and the die is squeezed together, I should use red, with force, it will, assuming that the die is much stiffer and stronger than the other material, and it won't deform as much in comparison to the blank material, you can actually just punch out the shape that you want. So sometimes we can use this for punching mechanisms, or even some sort of stamping mechanism where you don't go all the way through the material. That would be more like a surface peening, and I think we've talked about that before. Okay, let's look at drawing and extrusion. They're similar, but not quite the same. Drawing would be similar to rolling in that you have an initial plate that goes through, again, a die. The die is similar to the forging, where the die has a certain thickness that's desired, and we're thinning out the material. And but it's different than the rolling because the die isn't moving. You actually pull the plate through to achieve the final thickness desired. Okay, that would be not quite the same as extrusion, where you're still at this, remember, this is not necessarily at hot temperatures. You're not looking at molten metal here, but you have a billet of metal and you're actually pushing on it, pushing it through a die. So both drawing and extrusion use a die. Extrusion, you need often what we call a die holder, which is going to be like providing extra stiffness and strength. Let's just call it support to that die, so the die doesn't move, and you're pushing the material through. So we have a drawing, which is pulling it, extrusion, which is pushing it, rolling, which is rolling through, and forging, which is more of a stamping or a punching out option. So those are 4 common manufacturing mechanisms. These are very common, and this would be good information for an FE exam type question. So I'd be able to differentiate these. And then finally, we have down here our percent cold working equation, where we have an initial area, A naught, and the final area, A sub D, divided by the initial, and we get some sort of a percentage change is what we're really looking at in the overall area of that cross-section. That's going to represent an amount of damage that's going on with that operation, and it will change the strength of the material proportionally. Interestingly, we can see these dislocations happen, and the cold working make these actually when we take a look at the crystal structure itself. So like here's an image, SEM scanning electron microscope image of a material, looks like titanium, before and after. This is the after image where we produced cold working, and each of these lines is representative of the dislocations that have occurred inside this crystal structure. Okay, they start to entangle with one another during cold work. And this entanglement itself also adds to the motion becoming more difficult and the strength going up. We can calculate the density of this particular dislocation. Density during the cold working. We know that this density, the dislocation density, is equal to the total dislocation length, and we're going to divide that by the volume. So you could look at it in terms of the initial density and the final density by looking at the initial volume and final volume as well as the length involved. Okay, we see that deforming the sample will increase the density of the dislocations. We see that, and here's where it starts to become interesting. If we start to, after we've cold worked a material, if we heat it up afterwards in a fashion that we have prescribed, we're going to call it heat treatment, and we'll talk about what that is more in a little bit. We can actually remove these dislocations, and we can reduce the density of them, or we can, annihilate them altogether. Thirdly, the yield stress will increase as this density goes up. A neat feature of our Wiley Plus is that there is a video in Chapter 7, Section 11, that can start to see this annealing process. This process of removing dislocations by heat treating the material. So it's reversible. So go ahead and take a look at that video. They do a great job. Okay, after we've cold worked the material, we can heat treat it. And let's look at how that heat treating affects the properties of the material. In order to look at this, I guess I want to move back to the previous page for a second to be able to kind of lay out what we mean by annealing. Okay, so this is how I want to lay it out. I'm going to start on the left. If we have a billet of steel or some sort of initial material that is generally isotropic, meaning the crystals are about the same size, about the same, or same orientation in every direction, and we cold work it, meaning we've lengthened it, we've induced the damage to the crystal structure by lengthening it or in some fashion. What this has done is we've cold worked it. It creates inside that material, the crystalline structure now has elongated crystals. It has anisotropic behavior, as we've already looked at. We've looked at how the strength, let's use ultimate strength as a stand-in for the word strength. I don't really like that, but let's talk about that. Our strength has gone up, but there are other properties that have happened as a result. Okay, so we need to look at that and define what those are. And then when we take that same material, and maybe we don't like all of those changes to our materials, if we wanted to, say, heat it and hold it at that temperature for some amount of time, there's going to be another change to the crystalline structure. And we need to look at what that particular change is and how that process works. This is what we call annealing. We can change the amount of cold working, which will change the density of the dislocations. We can change the temperature, and we can hold it at different amounts of time. So the entire process of annealing is an engineering process to optimize the material to be whatever we want it to be in the end. So let's go ahead and look at what those effects are. We've already talked about tensile stress. Okay, this tensile strength I'm using as a stand-in, maybe ultimate stress for that particular strength. If we start here with a material that we've cold worked, so it's after cold working, and we have a very high tensile strength, and then we choose to hold it at some temperature that we're going to call annealing temperature, and let's use 1 hour as our time. Okay, what happens is it follows this blue blue path here, this, oh, by the way, on the x-axis, we're calling these recovery, recrystallization, and grain growth. This is kind of a way we can also use time for this axis, and that, well, it can be a proxy for time, or we can use proxy as a time for these particular regions. So as we hold it for that for an hour, what happens to this tensile stress? Well, it starts out really high, and then with time, our tensile stress goes down, and we end up with a much lower ultimate strength after doing this procedure, this annealing for an hour. Now, in the opposite direction, we have ductility as the other property we're going to look at. The ductility starts out low, and at the end, we end up with a very high ductility. Remember that we're talking about percent elongation? Go back and look at that definition if you need to. The effect of the cold working created high tensile strength, and it created maybe low ductility because those members with that high tensile strength become very non-ductile and brittle, right? It's very brittle here. And then over this process, we have regained our ductility, but we've lost some of our tensile strength. Okay, and it just depends on what we want. If we wanted that high tensile strength and we were okay with it being brittle, then maybe that's what we wanted. But if the process of manufacturing to be able to produce the end result object or the widget that you want in the shape that you want it, because we have to do something to the material to create that shape, whether it's cutting or welding or punching or those other cold working type manufacturing products, we end up with these particular changes in the material from what we had originally picked. And the cool part is that after you've done your manufacturing, you can put it back in the oven and anneal it, and you can regain the initial properties that you wanted. So that's where we say the effects of cold work are nullified. All right, I'm going to clear this page out for a second. That wasn't what I wanted. Okay, there, I found the picture again. And I wanted to erase the markings so that we can just look at these 3 annealing stages. When we have our time, the material is going through changes, and we can divide those changes into basically 3 stages. The first stage is recovery, the second is recrystallization, and the third is grain growth. Okay, so let's take a look at what each of those 3 stages means and what is happening during those stages. Okay, so I inserted a slide here where we define the recrystallization temperature as this higher elevated temperature at which the recrystallization process, all 3 stages, reaches completion in exactly or approximately just exactly 1 hour. Okay, and you'll notice that if we have T sub m, which we're going to call the melting temperature of the metal, this recrystallization temperature is somewhere between 30 and 60% of the total melting temperature. So we are not making this a non-solid anymore. It will remain solid. And for any given specific metal or alloy, we're just pointing out here that this temperature, what the temperature should be for the recrystallization temperature, depends on a couple different factors. How much cold work is actually within the material, and that as you have increased the amount of cold working, you decrease the recrystallization temperature. And then secondly, the purity of the material. Okay, so as you increase the purity of the material, you don't have to have it so high. Okay, so now that we've looked at and defined that, let's look at the actual mechanism. Whoa, what's happening here? Something didn't go right in this page. So I'll go ahead and try this slide by hand. Okay, so we're going to look at the initial material. So this is going to be fun. I'm going to be drawing a crystalline structure for a moment. And we'll talk about what does that look like with an extra plane of atoms. Let's see if I can speed this up for you. Okay, that probably sped it up for you a little bit. So what we're going to do is we're going to look at this in terms of, well, what happens when you have an extra plane of atoms, right? So I'm going to erase a couple of these right here in the middle. And put 2 in their place. Okay, so we're going to have 2 lines that had extra planes of atoms squeezed in here between the others. Okay, so I'm going to go ahead and mark those as blue. There you go. How do you like the blue dots? Okay, so this represents an extra plane of atoms on this side and an extra plane over here on this side. But what the end result was, remember where the extra plane is, you end up getting compressive stresses in those regions. We'll call those turquoise blue. And then you end up with tensile stresses in, you know, excuse me, I just knocked over the trash can. Tensile stresses in between the atoms in these regions. Okay, well, those tensile stresses tend to make the spacing between these a little bit bigger, and the spacing, as you can see here, is a little bit smaller. And so during recovery, what ends up happening, we have some, you know, extra atoms that can move. If you have a higher temperature, the atoms can move more, right? They can move a little bit more. They have the excitement and the energy to do so. And so they tend to migrate and they tend to fill in the crystalline structure. Ending up with at the end a fully annihilated dislocations. The crystal structure is back to the way it was before there was cold work. Thus, the properties end up being recovered. But this doesn't happen everywhere. This is just the beginning. And this is where we do have these extra atoms filling in that where they can, they do. But that's not all of the story. That's the first stage, the recovery stage. Let's look at the second stage. We're going to look at recrystallization. Interestingly, we are having, during this time phase, this part of the stage, we have material, new grains that are being formed. The old material, the cold worked material where you can see all the dislocations in there, we have reduced the dislocation density from the recovery stage. They're generally pretty small, and as a result, we can start with new crystals can be formed, like here, and that will continue to grow and consume up the atoms from the old crystals. So they will grow into these newly formed crystals that are more well-formed because there are no dislocations in them. This is the recrystallization phase. It ends after all the material, the original cold-worked material is consumed. As recrystallization continues, okay, so these are more pictures. we start with, these are the new little crystals that are showing up. And this is the old original one, or the cold work crystal, that is being consumed as it goes. You can still see the dislocations, and all of these little new crystals are starting to form. Once all of the material is consumed, and it looks like this stage over here on the right, then all of the big crystals gone, and we have completed our recrystallization.